Greetings, and it is my pleasure to welcome you again to this course on CFD. In this week, we mentioned we will have a demonstration of a working code employing different numerical strategies we learned during the last 7 weeks. The problem we consider to demonstrate is flow in a lid driven cavity. We listed in last module algorithm or steps involved in arriving at a code and numerical strategy. Step 1, grid generation, then discretization of the governing equation, solving the momentum equation to obtain intermediate velocities, solving pressure Poisson equation, then project the intermediate velocity onto a divergent free space using the pressure obtained through pressure Poisson equation, and repeat the above steps until convergence is ensured. Once we obtain results, then we look into the flow through different post processing and how to plot different quantities. The last 2 modules we basically did how to do a grid generation. Because the geometry is very simple, we considered uniform grid and structured grid, 4 by 4 mesh arrangement, and then we started doing something about governing equation discretization. We started with the u momentum equation. In the u momentum equation, we had diffusion term explained in the last module. In this module, we will particularly focus further on u momentum equation, considering the convection term, and then extend this procedure for the next momentum equation, that is v momentum equation. Continuation of the last class, whenever you solve momentum equation, we have to implement boundary conditions, and we define, because it is wall on 3 sides, for the primary variable u and v, we define no slip condition, and on the top wall we had velocity driving the lid as a boundary condition. And for pressure, we apply Neumann type of boundary condition, that is derivatives of pressure equal to 0. So, first we see how to implement boundary condition for u velocity. So, left wall u, and for left wall I is actually 1 and j running from 2 to j max equal to 0.0. On the right wall, grid in the x direction is I max, and again it is running in the j direction from 2 to j max equal to 0.0. Bottom wall, since for u node they do not coincide with the wall, we have to somehow ensure the no slip condition is also satisfied. So, we take average of north and south nodes, which indirectly will ensure the no slip condition is imposed on the bottom wall. So, mathematically it is u again at 1, that I is equal to 1, I max to 1 plus u 1 I max comma 2 divided by 2 is 0, which will result in u 1 I max comma 1 equal to minus u 1 I max comma 2. So, this way you ensure appropriate boundary condition imposed on the bottom wall. On the top wall, we mentioned lid is moving to the right with a velocity of 1 meters per second, and that is also ensured in a similar way, that is take a average. So, in this case now it is u 1 to I max, in j it is j max plus 1 plus u 1 to I max, and in j it is j max divided by 2, and that should be set to the desired velocity, that is 1.0. Now, you rearrange, you get expression u 1 to I max comma 1 equal to 2.0 minus u 1 to I max comma 2. Now, in terms of code, we see that u star, because we first do without pressure term included solve the u momentum equation. So, such a velocity is given superscript u star v star, because they are all predicted velocities. Then once they are corrected, they will be set to the actual velocity. So, this is done immediately after solving u momentum equation without considering pressure term. So, it is called u star. So, u star 1 comma 2 to j max in the j direction equal to 0. So, this is for enforcing boundary condition on the left wall. Similarly, the next line u star I max comma 2 to j max for j direction equal to 0. This is to impose boundary condition on the right wall, and similarly for bottom wall as well as for top wall. We have now explained in detail u momentum equation considering separately diffusion term and convection term, and how to enforce boundary condition. We will extend this procedure for the second momentum equation, that is v momentum equation. Without pressure term in the v momentum equation, the equation is written as shown here. Because we are solving without pressure term, the velocity is given superscript. So, it is v star minus v n by delta t equal to convection term from the left side is brought to the right side. So, u n dou v n by dou x plus v n dou v n by dou y with a minus sign, because it is brought from the left side, plus the viscous diffusion term as shown here. We mentioned we are solving explicitly. So, all the superscript for other quantities are with n. Last module we also mentioned the convection term can be rewritten as shown here. So, this u n is brought inside the partial derivative as shown here, that is dou by dou x of u n v n, plus again for the second term v n is brought inside the square inside the partial derivative. So, dou by dou y of v n squared plus the diffusion term. In the next slide, I am going to explain how this can be written and what actually it results. Consider the diffusion term first. So, diffusion term, that is nu dou squared by dou x squared of v n plus dou squared by dou y squared of v at nth level, and that we are using second order central differential scheme. So, the first term is for the x direction. So, we have I minus 1 comma j, I plus 1 comma j minus 2 times v at I comma j evaluated at nth level divided by delta x squared. Now, the second term is for the second derivative in the y direction, that is evaluated again using central differential scheme in the second direction. So, v at I j minus 1, v at I j plus 1 minus 2 times v at I comma j evaluated at nth level divided by delta y squared. We mentioned in order to have boundary conditions enforced, we should have ghost cells, that is they are not actually part of the grid that you have defined, but they are extra nodes in particular direction, and for simplicity we take those extra grid lines at the same distance as the original grid lines. For example, we define 4 by 4 grid lines. So, we have 4 in vertical line. So, 1, 2, 3, 4, similarly 4 in the horizontal. So, 1, 2, 3, 4. Now, for the v momentum equation, because we are following staggered grid arrangement of variables, we need to have one more extra grid line on either side as a ghost cell or ghost node. So, these are shown by red color line. So, this is in the left side and another one on the right side as shown here. Now, for simplicity sake, we define the delta x of the ghost grid line and ghost cell same as the immediate adjacent cell. Similarly, for the other direction, because V is in staggered grid arrangement, they are all stored along the horizontal line and they are shown in this picture with a full circle as shown here. So, this is for V velocity. Similarly, for these are all for storing V velocity. So, V staggered grid with the ghost cell for boundary condition implementation. We had a similar thing when we did U momentum equation, but it was in the j direction. Now, for V momentum equation, it is in the I direction. Because of this extra ghost grid or ghost cell, number of V velocity unknowns now becomes I max plus 1 into j max. So, corresponding code part of the code snippet. So, function V star old V equal to V momentum, and you have arguments defined as I max, j max, dt, dx, dy, Reynolds number, u v and old V. So, V star you define memory zeros I max plus 1 j max, connected term zeros I max plus 1 j max, and alpha is a new variable you define. If you can recall, we have unstudied term on the left side. So, V star minus V n by delta t equal to the convection term brought from the left side to the right side, and then we have a diffusion term. The diffusion term dou squared V n by dou x squared plus dou squared V n by dou y squared. So, if you discretize, we have delta x squared delta y squared, and this alpha is taking those terms, those coefficients appropriately. So, minus dt is brought from the left side and Reynolds number associated with the nu and delta x squared and delta y squared. So, when you write the diffusion term, we have alpha, and for the first term, that is dou squared V by dou x squared, we explained that we are doing second order central differential scheme. Then we have a corresponding terms here, that is V I plus 1 comma j, V I comma j, V I minus 1 comma j, and this should be divided by delta x squared, because alpha has both delta x squared and delta y squared. We multiply by delta y squared for the first term. Similarly, the second term in the diffusion term is dou squared V by dou y squared. If you write it in difference form, it is by delta y squared, and we are multiplying by alpha commonly. So, extra term is adjusted in the numerator as dx squared into the second order central differential scheme for the second term. So, we have V evaluated, V taken from I j plus 1 minus 2 V I comma j plus 2 V I j minus 1. So, once we get diffusion term explained, we will now move on to convection term. So, convection term is rewritten including the u multiplying and v multiplying into the partial derivative. So, it is dou by dou x of u n v n plus dou by dou y of v n squared, and we write in terms of north, east, west, south. So, we have u east at nth level, v east at nth level minus u west at nth level and v west at nth level divided by delta x. Similarly, for the second term, as v north from n time level squared minus v south at n time level squared divided by delta y. Now, if you recall what we learned in week 4 lesson, convection term treatment, we have a different approximation procedure, central differentiation type of approximation, pure upwinding approximation, quick type of approximation, power law scheme, hybrid scheme. So, in this we implement central differentiation type of approximation. So, u at east is evaluated from the neighboring nodes in this way. So, u I comma j plus u I j plus 1 by 2. Similarly, for the west, the corresponding west is I minus 1. So, u I minus 1 j plus 1 u at I minus 1 j divided by 2. Similarly, for v, so v at east is evaluated by central differentiation type of approximation. Similarly, for the other one, and also for north and south. So, once we define all this, we see corresponding code. So, for I running from 2 to I max and for j running from 2 to j max minus 1, because on the top, that is the last j, we have a boundary condition implemented. So, it is only up to j minus 1, u east, v east, then u west, v west, v north, v south, all are individually evaluated based on the expression that we have defined in the previous slide. Then all are put together as convective term I comma j equal to minus on for one term plus other term. So, these are individually written here, coefficients for d u v by dx, coefficients for d u v by dx and so on for each line. V momentum equation, because we are following explicit discretization, the computation of intermediate velocities becomes straightforward as shown here. So, V star minus V n by delta t equal to minus convection term plus diffusion term. So, we directly use, we have independently evaluated convection term, we have independently evaluated diffusion term. So, we directly use this expression to get what is known as a V star. So, V star is equal to V n plus delta t minus convection term plus diffusion term. So, compute the fractional step velocity, otherwise V star I for I 2 to I max and for j 2 to j max minus 1, V star is equal to V I comma j plus dt multiplying convection term minus diffusion term and n and n. As we did in u momentum equation, as soon as we solve particular equation by discretization procedure, we need to enforce boundary condition. We did that for u as u star boundary condition. Similarly, we should do for V star also. So, top wall V 2 to I max and j max equal to 0, bottom wall V 2 to I max comma j max equal to 0. Left side wall, since the velocity nodes do not coincide with the wall, an average of the east and west node is considered to apply the boundary condition. So, V 2 1 to j max plus V 1 for I direction and for j direction it is 1 to j max by 2 equal to 0, and if you rearrange you get expression as shown here. Similarly, on the right side wall, V for I it is I max, to represent it is the right side wall plus 1 and 1 to j max in the j direction plus V I max 1 to j max by 2 equal to 0, and if you rearrange you get expression as shown here, and this is what we enforce in the boundary condition code as shown here. Okay. So, boundary conditions are V star in the I direction 2 to I max and j is 1 equal to 0. This is for the bottom wall. V star again I 2 to I max j max equal to 0. This is for the top wall. Please recall, on the top wall we have imposed velocity driving condition, but that is only for u velocity and v velocity is set to 0. Now, for the left, V star 1 for I and 1 to j max for j equal to minus V star 2 comma 1 to j max, this is on the left side, Again we should recall what we did for u velocity on the bottom wall, because we do not have a node coinciding with that particular wall, because we are following staggered grid arrangement, we do not have a node coinciding with that wall, we need to have a rearrangement in such a way that boundary condition is actually enforced. So, for that only we have a extra ghost cell or ghost node. So, the average between the ghost node and the immediate node adjacent to the boundary condition location, that is the left side wall, is actually written in this form. So, V star 1 comma 1 to j max equal to minus V star 2 1 to j max. This is for node on the right of the left wall, and this is from the ghost cell. So, they are equated in such a way the boundary condition V is equal to 0 is enforced on the left side wall. Similarly, for the right side wall, again using ghost node and ghost cell, we have written line for enforcing boundary condition for V star. We did this in detail for u star in the beginning of this lecture. So, in this module we continued a u momentum equation for enforcing boundary condition. Then we repeated the procedure for V momentum equation. We considered separately convection term, diffusion term, and how to put them together to get V star. Once you get solution, we need to enforce boundary condition, and we follow the same procedure as we did for u for the right side, left side wall, and for the top as well as for the bottom wall. In the next module, we are going to talk about pressure term, projection method, and subsequently linking pressure and velocity. Thank you.